So, dear students, so today I'm going to discuss regarding the quantum gates. But before that, I'll be just doing the problem which I had done in the last class on the last video. So, which I have not completed. So, the question here is find the inner product of U is equal to 3 plus I and 4 minus I, and V is 3I 4I. Correct? Inner product. So, you have to find what UV basically. So, first thing is do what? The conjugate. Correct? Conjugate meaning plus will change to this, plus I will change to minus I. Minus I will change to plus I. Correct? Then take transpose. Transpose in the sense the columns will be converted here into rows respectively. So taken transpose. Correct? Then I will multiply with V. So first row into the first element here into 3I. Second element into 4. So 3 minus I into 3I plus 4 plus I into 4. So upon doing this, I'll be getting the answer. That's all. So it's a very simple process to get full mark in this. So now coming to our today's main session, that is quantum gates, but we have to know some formats before entering to this. So one of the thing is orthogonality. Okay. So we should always know what is zero, correct? And everything is represented in keto form, that is in 1 0, the column wise, not in the row wise. 1 0 and 1 is what? 0 1. So 0 to 1 is what? 0 and 1. So multiplying 1 0 into 0 1. 1 0 into 0 1. So 1 into 0 is 0 plus 0 into 1 is 0. So if we're getting the answer 0, then 0 is perpendicular to 1. So orthogonality meaning both the vectors, two vectors are perpendicular to each other. Orthogonality, the value will be always equal to 0. So if I get the value as orthogonal or 0, it is orthogonality. Okay, so suppose if I get the value as 1, it is called normalization or normalize. The vector is, suppose if I multiply two vectors and if I get 1 as the answer, then it is said to be what? Normalized vector. Normalized vector. Anyway, you'll be clear about it now. Orthonormality. 0 0. So 0 is what? 1 0 in and 1 0. 1 is in row, other is in column. If I'm getting the answer as 1, normalized. 0 1. 1 0 and 0 1. So row and column multiplication, I'm getting an answer as what? 0. 0 means orthogonal. But here again, 1 1. 1 1 is what? 0 1 and 0 1. 0 1 and 0 1 is 1. So it is normalized. 1 0. 1 0 is 0 1 and 1 0, that is 0, that is orthogonal. So we have two sets of vector which is orthogonal and two sets of vector which is normalized. That's all. Probability. Alpha of 0 and beta of 1. So obviously if you do alpha of 0, 0 is 1 0 and beta of 1 is 1 value is what? 0 1. So I'll get what? Alpha beta in the vectors. That's all. And the inner product, I'll be getting always alpha square plus beta square. No need to remove other things. Just remember alpha square plus beta square. And now comes our important thing, Pauli matrices, which we'll be using mainly in our quantum gates respectively. So yeah, coming to this, the Pauli matrices. Okay, so we got sigma 1, sigma x. X matrix is given as 0, 1, 1, 0. Sigma 2, the matrix is what? So we got three matrices x, y, and z. 0, 1, 1, 0, 0 minus I, 0, and 1, 0, 0 minus 1. Now, we got some properties of this Pauli matrices. Okay, so this is mainly Pauli matrices main idea is to show the spin. So we already studied about the spin quantum number, right? Yes, that is only about the Pauli matrices. So it just shows the what is the spin. That's all in this. So square matrix is always equal to my identity matrix 1 0 0 1. And if I square y square and z square, or whichever I square, I'll get the identity matrix. Then these are all unitary matrices. In the sense, if I'm multiplying, obviously I'll be getting the answer as 1 itself. Hermitian. Hermitian in the sense complex conjugate. Okay, I think we already discussed Hermitian in the last video. Correct? So first you take the complex conjugate, that is changing the signs of the I, and then converting rows into column or columns to rows respectively. That's all. So that is what been written over here. Just changing the signs. Y value is this 0 and minus I 0. So I'm just changing the minus I value as I and I value as minus I. Then transforming rows to columns. That's all. Simple procedure. So we have to do these things fast so that it will be there in our mind. If we take it very slowly, this will vanish away just like that. Operations of polymatrices on zeros and one state. So x of 0. X of 0 means always multiply by what? 1, 0. If x of 1 means what? Always multiply by 0, comma 1. So once you multiply it, you will get to know the answer. And so this is our NOT gate also. So coming to this is also called bit flip gate. Bit flip gate. So similarly, you can do for Y and Z. Y and Z you have to do. Now coming to our quantum gate. Yes, so quantum gates are nothing but what? It's a very simple computing device that it performs quantum operation on quantum bits. Okay, fine. So let's see the single qubit gate. 0, 0 is 1, 0, 1, 1. So it has got type of gates which we learned in our Boolean algebra, not or XOR and all. No. So similarly, we also have such gates here. Here it is what X gate or quantum NOT gate. So x of 0 should be what? Always equal to 1. X of 1 should be what? Equal to 0. This is, if this becomes this, then it is a NOT gate. Because 1 we all know what? 0 and 1. Correct? 0 and 1. But if I'm getting the answer as 1, 0, obviously the complement of it, NOT gate. So as I already told you, bit flip gate. Already just now discussed, NOT gate. Above I just told it is for the x1. Yeah, bit flip gate already I told here. The truth table 0 to 1, 1 to 0. That's all. Again, coming to the Y gate, 0. The output is what? I of 1. Correct? 1 is minus I of 0. Alpha of 0 plus beta of 1, I'll be getting out I alpha of 1 minus I beta of 0. In the sense, we have to just do the operation. See, again, this can be done. Very simple thing. Y value already we have discussed 0 minus I comma 0. Correct? Y of 0. So multiply this with what? 1 comma 0. Then do the normal matrix multiplication. Correct? Then you'll be getting 0 I. If you take I outside, you'll get 0 1. So I of 1. So if I'm getting 0, I'm getting what? I of 1. So all of those things are only been put into truth table. So once you multiply, you'll get the answer. Simple matrix operation. Similarly, Z also. Similarly, Z2. Then coming to H gate or Hadamard gate. Okay. So again, coming to this, we got the operation 1 by root 2, 1, 1, 1 minus 1. So coming to this, first h of 0 multiply with what? 1, 0. I'll be getting 0 plus 1 by root 2. If I put h of 1, instead of this plus, minus will come. 0 minus 1 by root 2. Correct? Yeah. And if it is superimposed or superposed qubit, that is nothing but 1 by root 2, 1. Just put the matrices alpha and beta here. Correct? I'll be getting what? Alpha of 0 plus 1 by root 2 and plus beta of 0 minus 1 by root 2. So you no need to do these operations. Directly you can, if you know it, you can directly write it down. But make sure that you write down the truth table properly. Phase gate. Okay, it's a single qubit gate, S gate, I'll say. S of 0 into 0. So S is nothing but what is the value? 1, 0, 0 I. First thing is S of 0. So multiply by 1, 0. I'll be getting 0. Next one is what? S of 1. Multiply by 0, 1. I'll be getting this matrix. I of 0, comma 1. If 0, comma 1 is what? 1. If it is 1, comma 0, it is 0. That's all. So again, we have to know the truth table. So here it is alpha of 0 plus I beta I of 1. I beta of 1 or beta I of 1. You can write it as it is. Alpha of 0 and beta of 1. T gate. T gate is also called pi by 8 gate. So 1 0 instead of 0 1, I'll be ready e power I pi by 4. E power I pi by 4. So first thing is T of 0. So multiply by what? 1 comma 0. I'm getting 0 as answer. Next one is what? 0 comma 1. If that is should be T of 1. Here it is written T of 0. Just make sure that it is T of 1 here. So I'll be getting e power I pi by 4 into 1. That's all. So remember the output. Truth table we have to remember for all the gates. So single bit operation is over. Now it's all about 2 bits. Yeah. So first one is C naught. So here we can see it is not a simple thing. Here it is what A comma B gives A comma B exclusive A. A exclusive B, meaning we already studied this in our lower class. A exclusive B is something but what? A bar B plus A B bar. Okay, the same thing only we are using here also. Yeah. So coming to this AB input at A as output, correct? So B exclusive A. So if it is 0 0, I'll be always getting 0. If 1 is 1 comma 1, I'll be always getting as what? 0. Correct? So in the sense here, what it is written here, this is C naught. 1 1 should be 1, right? Correct? But I'll be getting what? 0. Okay. So A exclusive B, if I want to just show you here, A bar B plus AB bar. So A bar, I'm taking the first one, 0 and 0 complement is what? 1. 1 into 0 plus AB bar. A is what? 0. B bar is what? 1. 0 plus 0, I'll be getting 0. That's how I'm getting this 0 here. B exclusive A. Okay, B exclusive A. I'm getting like this only. A exclusive. It's better to know these things. So 0 0 is 0 0, 0 1, 0 1, 1 0. So only the last two are interchanged. 1 1 and 1 0 are only interchanged respectively. Swap gate. Again, it is a 2-qubit operation. Swap. I'll just show you the thing. Yes. So coming to the truth table here again, AB and A comma A exclusive B. Then this is taken as the input and we'll be getting the output as what B comma A exclusive B. And then this is taken as the input and we'll be getting B comma A. So here only the second and third. Only the second and third is getting interchanged. The rest, first and last is same. First and last is same. So I think it's clear. So if you know truth table well, we can do it properly. And coming to this one, what is it? The Z, correct? In the Z gate, only the last one is interchanged. Rest, no change. Rest of the input and output, there is no change. Only last one is interchanged. The minus sign is because it is flipping state from 1 to -1. That's all. It's flipping state from 1 to -1. So make sure that you draw the table and the diagram neatly for the gate problems. And for the Toffoli gate, so this is a 3-bit. Okay. Yes. So out of which two are control qubits and one is target qubit. So we can see here the diagonal 1, 2, 3, 4, 5, 6, 7, 8 are there. Correct? Except the last two diagonals are all 1. So this you have to remember it. And then obviously the gate representation in this. Yeah. Coming to truth table, everything is same except the last two. Last two are only different. Rest everything is same. So make sure that we know the truth table properly. Okay. So that's it. So that's it for the today's session. Thank you.